My dear friends, welcome to Rajashekar classes on applied data science with Python. This is lecture number 634. In this lecture, we will try to understand code example MNIST dataset. Let's go to our favorite MNIST example. In the previous lectures, we saw MNIST with lots of types of MLPs, isn't it? Now, let's see what happens on MNIST dataset which we use convolutional neural networks. Remember, MNIST dataset is an image dataset of size 28 by 28 pixels. Just try to recall, this is handwritten characters. Basically what it is, it's handwritten characters. Since it is an image, I can obviously use, as it is an image dataset, we can obviously use convolutional neural networks on top of it. As it is image, I can obviously use convolutional neural networks on top of it. If you just see, if you there is a link here, GitHub link. If you click on it, you will get you have already written code is available in GitHub. I request all of you just go through this particular link so that you will get this particular code. It is very straightforward code. We are importing bunch of libraries. Just see, this is the what's happening here. We are importing bunch of libraries. We are defining what is batch size. Just see, what is the batch size? Batch size equal to 120. What is the batch size? It is a 10 class classification problem. Just see here, num underscore class equal 10 means it's a 10 class classification problem. I am training it for 12 epochs. Just see, epochs equal to 12. What does it mean? I am training it for 12 epochs. My image size is, if you check, my image size is 28 by 28. I am loading whole MNIST data here. How can I load? Just see, I am MNIST dot load means I am loading whole MNIST dataset here. Once I am loading all of my data, of course, normalizing the data. How can I normalize? Just say this is a sample code for normalizing the data. You can see data pre-processing steps. The core thing comes here. I'm defining sequential model. Just see, what is this model equal to sequential means what? You are defining sequential model. My first layer is convolutional layer. Just observe this one, model dot add con2d convolutional layer with my first layer is convolutional layer with ReLU activation. My second layer is again a convolution. It's a convolution ReLU activation. Then max pooling. I'm doing. If you observe here, I'm doing dropout. I'm doing flatten and add dense. Add dropout, add dense. You can see dropout, flatten, dense connection, dropout, and dense connection. Very simple. This is almost, you can read it here. Very small connet that I am building, but this is only for tutorial purpose. I am not using any other existing models. I am not using any other existing models like VGG16. Also, I am just building a small convolutional neural network on my own. And of course, I just say compile a model.compile, isn't it? I want to minimize my categorical cross entropy, which is the multi-class log loss. We are optimizing using ADA delta. You can use ADA delta or ADAM, anything. And I will also want to measure accuracy, isn't it? How can I measure accuracy? Just see here, metrics equal to accuracy, isn't it? What is metric? Which metrics am I using here? Accuracy. By the way, this whole code has been sourced from GitHub examples. Just see, this code is taken from GitHub examples. The Keras team actually created bunch of examples. One example is how to apply. One example is how to apply convolutional neural networks to MNIST. We have taken the code and pasted here and literally just run it. We have not written this code. That's important. We have not written this code. When you run it, it takes few minutes. It takes few minutes to run, but you will quickly notice that it is converging. Look at the validation loss. Just observe, if I run this one, what will I get? Just see this. These are the outputs, isn't it? Notice that it's converging. Look at the validation loss. This is you can see the training loss. Just see you have training loss, you have training accuracy, validation loss, and you have validation accuracy, isn't it? Just look at how fast you are converging from one epoch to other epoch, even after just finishing, even after just finishing the first epoch. I am getting 97.6 accuracy on the test data. This is the power of convolutional neural networks. If you look at multi-layer perceptrons, if you look at MLP, we have to do 15 epochs to reach this accuracy numbers like this. In Cornet, because you are leveraging, because you are leveraging the image processing and convolutional operators, which are very useful in the case of images. Just with one epoch, we are achieving 97.6 accuracy, and by the end of the 12 epochs, you are almost reaching 99.927 accuracy. This is like terrific, almost like 100% accuracy for all. I can say 100% accuracy for all practical reasons. That's the power, especially when you have images. Of course, you can flatten this image. You can flatten this image and train multi-layer perceptrons on top of it. Better is you basically train convolution neural network on this, because Cornets has convolution operator which can leverage the structure in image like edges, shapes, etc. So while you solve the same problem using multi-layer perceptrons, MLPs, Cornets will be significantly very fast. As you have seen, just one epoch we got accuracy that got the 15 epochs in MLPs. MLPs took 15 epochs, but whereas in Cornets it takes only one epoch. And using Cornets makes sense. So Cornets has special architecture. That's important. Cornets has it's a special architecture designed specially for image datasets, and it is inspired a lot from biological visual cortex of mammals like rats, monkeys, cats, and humans. And that's why they perform very well. So this is very simple code example. You can copy this code into your own Colab or Jupyter notebook and just run it, see how it runs. You have to be patient for some time. It takes little while to run. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.